Okay, um, here I am. We're kind of in our last unit, our last lesson before we test. We're put everything together and talk about curve sketching. Um, and when we do, there's a lot of different pieces to keep in mind. Um, Specifically, it's always good to think about domain of a function. For example, if it's 1 over x minus 2, x cannot be 2 in that scenario, or if it's the square root of x, and x must be greater or equal to 0. If it's a polynomial, then it's all real numbers. The range is, your outputs, what's happening for your outputs from your domain. Intercepts, so, if the x-intercept happens when y is equal to 0, and the y-intercept happens when x is equal to 0. Those are great points to be able to plot. We spent many times looking at those in previous classes. I'm not going to worry about symmetry so much, but asymptotes, especially if you have like a rational function, you might have some vertical and horizontal asymptotes that you have to keep in mind. Intervals of increasing and decreasing. Remember, we are increasing if f prime is greater than 0, and we're decreasing if f prime is less than 0. Local max happens where f prime goes from positive to negative, and local min happens where f prime goes from negative to positive. Concavity, it's concave up if f double prime is greater than 0, and it's concave down if f double prime is less than 0. And one thing that we missed here is our inflection points. Inflection point happens when f double prime changes sign. And finally, the end behavior of our function. So what happens as x goes towards positive and negative infinity? So this might be an asymptote, and it could just be, headed off like a polynomial. But the question is, what happens as you continue on towards infinity? Okay, so we'll think about that as we move along here. So let's start with this function, x cubed minus 2x squared minus 3x. The first thing I'm going to do is I'm going to just try to identify x-intercepts. Okay, and I can see right away the y-intercept. If I plug 0 in for x, I get 0 for y. And if I go to factor this, I get x times x squared minus 2x minus 3. So x times x minus 3 times x plus 1. And so you can see in that situation, we have intercepts of 0, 3, and negative 1. So we already have a good idea about what this function looks like. But we want to consider even more. And so as we consider intervals of increasing and decreasing and points of local max and local min, we're going to look at our first derivative test. And just please note that all of your work on your test must be confirmed this way. F prime of x is equal to 3x squared minus 4x. Make sure I've got this. And then minus 3. And I know that shape. It is a parabola. Unfortunately, it does not factor. I would need to use the quadratic formula. Some of you have it plugged into your calculator. Negative b plus or minus square root of b squared minus 4 times a times c, all divided by 2a. Oh, it doesn't factor. I didn't think it did. But I mixed something up. Oh, sorry. 4 times 3 times negative 3. There we go. Sorry about that. Try that again. 4 plus or minus square root of b squared is 16 minus 4 times a is 3 and c is negative 3, all divided by 2a. Wow, struggling. So 4 times 3 is 12 times negative 3 is going to be negative 36. Plus 16 is going to be 52. So I have 4 plus or minus the square root of 52, or 4 roots of 13. Sorry, 2 roots of 13 over 6. And I'm going to make those into some decimals so that I can see what's going on. Parentheses, 4 plus 2 roots of 13 divided by 6. We get 1.86. And then 4 minus 2 roots of 13. If you do it like that, make sure you press enter first. And then divide it by 6. And we get negative 0.54. And so that's what we've got. As you consider this graph crosses at 1.86 and negative 0.54, it's a parabola that goes up. And so we could consider that the function is going to be increasing from negative infinity to negative 0.54 union 1.86 to infinity. It will be decreasing from negative 0.54 to 1.86 because that's where it sits below the x-axis. A local max happens when it changes from positive to negative. And so that will happen at negative 0.54. A local min happens where it changes from negative to positive, 1.86. So I'm going to go ahead and plug those into my calculator to come up with the y values, because those are coordinates. I have x cubed minus x squared. I'm sorry, is it 2x squared? I can't remember. Let's see here. 2x squared minus 3x. As I go to my table, I type in negative 0.54. I have a y value of 0.88. As I type in 1.86, I get a y value of negative 6.06. All right, that's our first derivative test. Let us consider our second derivative. Our second derivative, f double prime of x, is equal to 6x minus 4. That's going to cross the x-axis at 2/3. Graph is going to look like that. So it is negative from 0, or negative infinity, to 2/3. However, it's below the x-axis. That's where the second derivative is negative. And it will be concave down. Concave up from 2/3 to infinity. It is at 2/3 that you have an inflection point. We go ahead and take our calculator and we plug in 2/3, or 0.666, repeating, and we get negative 2.59. This is not a rational function, it's a polynomial, so it does not have asymptotes. But the end behavior, the limit as x goes to infinity of the function, as you consider this polynomial, it's a cubic and it's positive, so therefore it ends up and it starts and ends in opposite directions. That's the behavior of that cubic. So the limit as it goes to infinity is infinity. As x tends towards negative infinity in the other direction, f of x will go towards negative infinity. So that's the end behavior. That's what it does. So people were a little bit maybe critical of my graph the other day. I'm going to point out Dominica here. That's all right. I won't take offense. 2, 4, 6, 8, 10. -2, -4, -6, -8, -10. And then over here, our x values, it looks like if I go over to about 4, that'll be sufficient. We'll go 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so I'm going to plot some really important points. First of all, I have intercepts of 0. I also have an intercept at -1. I have an intercept at +3. I have a local max at -0.54 and 0.88, which should be about right there. I have a point of local min at 1.86 and -6.06. I'm going to call that right about here. I have a inflection point at 2/3 or 0.66 and -2.59. I'm going to call that right there. We know it starts down, because we said it tends towards -infinity. Local min. Okay, so I tried really hard to get that graph to be just perfect. We're going to check it against what I have. We check out our window. My x min will go to -6, +6. That's about what I have up on the board. The y min of -10. Go -12 just because I go a little bit higher on the board. Tick mark every 2. I check out my graph. Compare it. Not too bad. I'm pretty good. You know, you're trying to make an excellent graph. Maybe if I change that window, if I wasn't so aggressive to the -12, I went to the -10 and 10. Would that just look a hair better? Yeah, probably. Yeah, not gonna lie, it's pretty awesome. So there's your complete graph, curve sketching. Make sure you get it all together. We're gonna do one more, and then we'll have a separate video. The difference here is that this one happens to be a rational function. And as a rational function, if we consider the intercepts, here, for example, if you want the y-intercept, you need to set x equal to 0. Watch what happens when you set x equal to 0. You get 0/2, which is 0. And then when you set the function equal to 0, so you have 3x over x plus 2. If you're going to make that equal to 0, if you would just cross multiply, you get 3x is equal to 0. So notice it's just wherever the top is equal to 0, and that would be at 0 as well. So we do have zeros there. Hopefully you understand that with the domain, x cannot be -2. So for your asymptotes, in this situation, you are going to have a vertical asymptote of x equals -2. You're also going to have a horizontal asymptote. The reason why I know that is if you find the limit as x tends towards positive or negative infinity of 3x over x plus 2, notice as you factor out the x out of the top and the x out of the bottom, and the x's cancel, and that goes away, you get 3. So it literally has a horizontal asymptote, as we've talked about before, y is equal to 3. So already I have a pretty good idea of this graph. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. The horizontal asymptote heads through 3. The vertical asymptote through -2. And that's what I have. Now, to figure out the rest of it, we know that there's this, the intercepts are at 0. But to figure out the other characteristics, let's find the first derivative. And I must use, in this case, the quotient rule. Derivative of the top is 3 times the bottom, x plus 2, minus the top times the derivative of the bottom, which is 1, divided by the bottom squared. I get 3x plus 6 minus 3x over x plus 2 quantity squared. or 6 over x plus 2 quantity squared. Now, what's interesting about this is the top is never equal to 0. The bottom is equal to 0 at -2. So that would be the only spot that you would check for a number line test. We're not going to look at the graph. We're going to consider the number line test. But consider this value. The bottom is always positive, and the top is always positive. Doesn't matter what you plug in, you're always going to get positives. What that means is that this function is increasing from -infinity to -2, union -2 to infinity. So we can't include -2 because -2 is not part of the domain. It's never decreasing. It never changes from positive to negative, so there's no local max. It never changes from negative to positive, so there's no local min. And there we have it. That was easy. Let's check f double prime of x. If I check f double prime of x, I'm going to rewrite this as 6 times x plus 2 raised to the -2nd power. So then I can use the chain rule. Look at that nice trick. 6u to the -2 and x plus 2. The derivative of x plus 2 is 1, and the derivative of 6u to the -2 is -12 over u cubed. So I have -12 over x plus 2 cubed. Again, the top is never 0, but the bottom is 0 at -2. Let's test some points. I'm going to plug in -3. -3 plus 2 is -1. Cubed is -1. -12 over -1 is positive. Now I'm going to try plugging in 0. 0 plus 2 is 2. Cubed is 8. -12 over 8 is negative. What that tells me is that this function is concave up from -infinity to -2. It's concave down from -2 to infinity. There's no inflection because people say, well, it changes sign at -2, but -2 is not part of the domain, so we cannot count it. So as you sketch this graph, notice it's concave up in this region, so it's going to look like that. And it's concave down in this region, so it's going to look like that. Notice we said it's always increasing, and this function, it's always on its way up. And so that confirms the graph of this rational function. I do just want to show you one last thing, as I do find it very interesting. Notice the function was 3x over x plus 2. Last year we talked about taking x plus 2 and dividing it into 3x. What do you multiply x by to get 3x? You multiply by 3. 3x plus 6, subtract, and you get -6. So 3 minus 6 over x plus 2. Or in other words, -6 over x plus 2 plus 3. So what that told us is that there's a vertical shift of +3. Look at my graph. Vertical shift of +3. We said there's a horizontal shift of -2. Look at, we're back 2. We also said that because of this negative, you know that there's a vertical flip. Notice that they are in opposite quadrants from what they would normally want to be. So it does connect exactly with what we've done in previous years. 2 excellent problems, both a polynomial as well as a rational. That's your first video. We'll get the second one going with just a couple more, a little bit more challenging problems. I don't think I'll do the last one, but I will do this one. See you in a while.